right, good evening, everybody, and welcome. I think we've got a very interesting topic this evening with Ilani Loebshaw. I mean, something that's called monsters of the universe has got to be interesting. So we're going to hear her talk and then afterwards have a question and answer session. If you, Ilani, just a quick question. If somebody wants to ask a question during the talk, do you mind? So can they put their hand up?
No,
I don't mind.
No, I don't mind during the talk. I might not see it if somebody puts up a hand. So they might. Well, I also don't mind it if they interrupt me.
All right. So I just want to ask people if they want to ask a question during the talk, just put up your hand, and then I will manage the situation. Otherwise, it can get chaotic. But preferably ask your questions afterwards. If you can write them down, remember them. Okay. So without much ado, then Ilani, welcome and go ahead with your talk.
Thank you very much. So I'm sitting in Potchefstroom at the moment, and it started raining, well, last night for the first time since April, so it's still raining. So I hope it doesn't get too noisy. But I want to talk about the most massive galaxies in the universe. So this is the central cluster galaxy. So if you have a cluster of galaxies, so it's hundreds of galaxies that's gravitationally bound. Almost always in the center of the cluster, you will get these absolutely massive elliptical galaxy, and it's called central cluster galaxies or brightest cluster galaxies. And I'll talk a little bit about how they get to be so massive. But I also want to talk a little bit after that about how we use SALT and MeerKAT to observe galaxy clusters. And I'll talk a little bit about the Fornax cluster project, where we're using both SALT and MeerKAT simultaneously. Okay, but let's look at the massive galaxies. So, 13.9 billion years ago, you had the Big Bang. And then you started to form stars after a while, and then the first galaxies. And then you started to form bigger structures. So the first galaxies merged and formed bigger galaxies. And as you come closer to the present day universe, the structures that you form are larger. So you form the largest galaxies. And in close to the present day universe, you start to form big clusters of galaxies. So the largest structures in the universe assembled late, it doesn't mean they're very young. So the stars that ends up in these galaxies already formed very early. So the stars are quite old, but the structures in the galaxies and the galaxy clusters assembled quite late. So you can also look at this through computer simulations. So we run this simulation in Potchefstroom Northwest University. So you can simulate a small box of the universe, a cosmological simulation. And then you can track it through time, because this is, of course, something that you cannot do in observations. In observations, you just get one snapshot of what it looks like at this moment for us. So this is the first picture is when the universe was about 13 million years old. So you can see it shows the density map. So there's some areas where you have more dense material than other areas. And as you go on, so here the universe is about 1 billion years old. Now you really start to see the structure forming. But you can see that the structure sort of form where you're at the highest density material. And as these structures form, that's where it grows, because obviously that's where there's more mass and a bigger gravitational pull. So this is where you will form the bigger structures. And this is at about 3 billion years. And this last image is about the present day universe, 13.9 billion years. And then you can see in these filaments, they're all connected. And then you can see these clumps. So this is where you would form clusters of galaxies and the most massive galaxies. So if we look at them just by eye, this is a collection of some of these brightest cluster galaxies. And they look quite yellow, right? So they're elliptical galaxies, and the stars are quite old. So they look yellow reddish. But if we just, for a reminder, if you look at galaxies in different wavelengths, you see different components of the galaxy. So this is a whirlpool galaxy, a typical spiral galaxy. And if you look at with the radio telescope, you mainly see the cold gas, so the neutral hydrogen. And in the infrared, you see cool stars, and in the ultraviolet, you see hot stars. And in the X-rays, you see the hot gas. So in all the different parts of the electromagnetic spectrum, you see the different components of the galaxy, and you want to put it together to understand what's going on, the physics in the galaxy. So if we look at these galaxies that look sort of red and dead a bit more carefully, some of them are actually extremely active. So if we zoom in a little bit and you look at these galaxies in different wavelengths, in the radio and UV and infrared, then they show almost all of the signs of extreme star formation in some cases, or at least extreme physical processes. So they're actually quite active, but not all of them. This is only a small number of them. So what is happening in these galaxies is if you have cold gas or a gas reservoir, and the gas can cool down under certain conditions, then you can start to form stars. And that is one way that the galaxy grows and builds up its mass. But as you form stars, the young stars also have stellar winds that heat the gas up again. And the same gas reservoir also feeds the black hole in the center of these galaxies. So all of these massive galaxies have supermassive black holes in the center. So the same gas sort of accretes onto the supermassive black hole, and they've got jets that also heat up the gas again. So it's this very delicate self-regulating cycle of cooling and feedback and heating of the gas that sort of regulates the star formation in the galaxy, that you don't form, well, too many stars. So this is one way in which these galaxies grow. But the biggest way in which they grow is just because they're so massive. So they're at the gravitational center of the cluster, and they pull in all of these little satellite galaxies, and eventually, they will just merge with the nearby galaxies, and they will grow larger. So this is their main mechanism of growing the stellar mass. So if we talk about massive galaxies, how massive is a massive galaxy? So it's about 10 to the 12 solar mass. So if you write it out in kilograms, it's a lot of zeros. So it's a number that I cannot wrap my head around, but it is extremely massive galaxies. And the thing is that obviously they call it cannibalist. So the more they eat, the larger they grow. But almost more importantly, the larger they grow, the stronger the gravitational pull will be, and the more galaxies will merge with the gravitational, with the central galaxy, and it will just keep on growing. So that's how you get these absolute monster, humongous galaxies in the centers of clusters. And they're extremely interesting to study, both for this, well, these merging processes, and also this cooling and feedback, heating of the gas process. Tells us a lot about the physics of some of the fundamental processes in the universe. So if we look at some of the questions that we would like to ask in our research, it's like I said, it's not all of these galaxies that form stars, but some of them are extremely active. So we would want to know under which conditions can you get star formation? Does it have to do something with the environment? So the cluster that the galaxy finds itself in, and then also the star formation rate, for example. How much stars can they form and still continue the self-regulated feedback loop? So this is some of the questions that we've kept ourselves busy in my group for the last 10 or so years. And if we want to study it, you can approach it from different angles. But what we do, or what I spent most of my time on, is optical spectroscopy. So you can take an optical spectrum of the galaxy. So if you have this galaxy edge on this galaxy, for example, here you can put a slit on and it goes through a spectrograph and it disperses the light and you get a nice optical spectrum. Or these days, what is much better, but it's much more complicated and also much more difficult to get time on telescopes for it. But this, if you can get a cube, so it's called integral field unit. So your data comes out in a cube and you've still got like an X and a Y, so you still have an image, but every pixel in the image in the third direction is a spectrum. So you can make cuts at different wavelengths and you can see what the galaxy looks like at different wavelengths, and everything that you can measure, you can then make a 2D map of that. So this is the two main ways that we can take spectra. And what you can see is for this spectrum, for example, this is just the absorption spectrum, so that comes from the stars. And what you can learn is, of course, elemental abundances. What sort of elements do you find in the stars? We can learn about, and I'll talk a little bit more about that, is we can learn how, at what times these stars formed. So we can do stellar population modeling, and we can also look at the orbits of the stars, so how they're moving. So this is all information that's encoded in an optical spectrum like this of a typical elliptical galaxy. And then you can also get, if there's gas in the galaxy, at some of these lines, for example, the Balmer lines, the hydrogen lines, you will get emission lines from the warm gas. And from that, if you study the emission lines from the same spectrum, you can study the warm gas. So you can see what sort of physical mechanisms heated the gas, how the gas is moving, is it connected to the way the stars are moving in a galaxy. And this is the type of thing that you can learn from optical spectroscopy. So the telescopes that we used, in the past we used a lot of Gemini North and South. So North is in Hawaii and South is in Chile. And we also used the VLT in Chile. And it's got an extremely nice instrument. It's called MUSE, that gives you these data cubes, these integral field cubes. And that's what the instrument looks like, but it's extremely competitive to get observing time on MUSE. And then there's our own telescopes. There's SALT in Sutherland, and then there's MeerKAT, which is a radio telescope. But I'll talk a little bit about that, how we combine the radio data with the optical data in the second part of the talk. But these are mainly the telescopes that we use. So when you get a spectrum like this, very few of the galaxies that we can see, you can observe individual stars. So that's almost just a local group of galaxies. As soon as you go beyond the local group, then you can't distinguish individual stars. So the spectrum that you get is just the integrated spectrum of all the light from all the stars in the galaxy. So you have different types of stars. You have main sequence stars, red giant branch stars, white dwarfs, different types of stars. And luckily we know stars quite well, and we know what their spectra looks like and what sort of flux they contribute at what wavelengths. And we can decode an optical spectrum a little bit, but it's still very complicated because you also get, apart from the light from the stars, you also get a light from, well, anything that can emit or scatter emissions. So dust, gas, anything else will be, all of that information will be encoded in one spectrum. And we have to deal with that because even if you build, I don't know, a 100-meter telescope, the number of galaxies that you would be able to resolve individual stars are very limited. So if we want to study galaxies, we have, in the optical, we have to deal with building models to pull apart these spectra so that we can understand the different components. So this is basically what we do, is if we observe a spectrum, we want to fit it with a model, and you have different components or ingredients that go into the model. that I don't want to spend time on it. I just want to bring the point across that it's a complicated process to build up a model that you can match to your galaxy spectrum, and then you can try to infer what happened to this galaxy in the past as it formed its stars or its star formation history. Because you can only see a snapshot of a galaxy, and you can observe galaxies at different redshift. But that's also a time expensive way of studying galaxy evolution. So most of the time they call this galactic archaeology, where you just look at an integrated spectrum and you try to pull apart what happened to this galaxy in its past, the history. So typically we can do something like this. These are real spectra from some of these brightest cluster galaxies. So this is one spectrum, and then you can make up a model. So you can say, let's see what happens if most of your stars are very old, like 10 billion years old, but very recently you had a burst of star formation. And then you can make a mock spectrum, and then you can see how recently and how big of a star formation episode you need to make a spectrum that basically looks like what you observed. And you can do this for different scenarios. You can get a single burst of star formation or repeated bursts, and you have to build models that would hopefully match your galaxy spectrum. But there is, of course, a lot of assumptions going into this, so that's also where we have to spend time to understand it. So we also want to, if you now looked at the star formation history of these galaxies, I mentioned that only some of them actually form stars. So now you want to look at the cluster environment and say why only some of these galaxies form stars. And it has a lot to do with the environment that they find themselves in. Also, I don't want to go into too much detail, but it has to do a lot to do with the gas, if the gas is allowed to cool, and the time scale that the gas can cool. And if it's cool enough, then you would almost always find star formation in these galaxies. So we try to connect that what we learn from the galaxies also to that what we see in their environment to understand why, well, only some of them form stars. So this is over the last decade, what we've studied on this particular topic is how much of these galaxies form stars, these brightest cluster galaxies or central cluster galaxies, how we can constrain how old the stars are and how much stellar mass comes from young stars and old stars. So basically the star formation history. And then we try to link it with what we know about the environment. So physically why star formation can occur in these galaxies where you would really not expect star formation in a massive elliptical galaxy. Okay, so this is just an example of what the cubes actually look like on Muse data. So Patricia worked with us in Potchefstroom, is now in Portugal. But this is an example of what you can learn from the cubes. So if you have a spectrum and you can say, let's look at what the galaxy looks like around the hydrogen line, you can make a 2D map of this galaxy. And here you can see, and bear in mind, this is this massive elliptical galaxy that looks just by eye, if you just look at it, very yellow, red, and dead. But you can see these clumps and this ring of star formation around this galaxy. And this is why it's extremely useful to get cubes, that you can get this sort of 2D information of where in the galaxy are you actually forming stars. And this is another interesting example. Again, if you just look at the galaxy, you would really not expect this much structure, but you can see, if you look at certain lines, you can see all of these fine filaments, that's star formation or ionized gas around the galaxy. So that's what you can learn from the gas, but you can also learn from the stars, obviously. And all of these things that we can measure we can make sort of maps like this. So this is just an example of the kinematics of the star, so how it moves, the orbits. And you can see from this first plot, the galaxy is rotating a little bit, so part of it is moving away from us, and part of it is moving towards us, which is again something unexpected for these massive elliptical galaxies. Okay. So then I want to talk a little bit about one cluster in particular, the Fornax cluster, and that we use the South African facilities, SALT and MeerKAT, to study the cluster in a lot of detail. So this is again the two telescopes that we have a lot of access to, and it's two of the best telescopes in the world in their respective categories. So it's the best optical telescope in the Southern Hemisphere. And at the moment, it's the most sensitive radio telescope in the world as well. Okay, so as you look at different types of galaxies, this is a spiral galaxy like our own galaxy, the Milky Way. And then as you go to denser environments, galaxies start to look different until you get in a cluster environment where almost all of these galaxies look sort of red and dead. And most of these galaxies start out as spiral galaxies with a lot of gas. So in this dense environment, something needs to happen to transform this galaxy from a nice blue star-forming spiral galaxy to a red elliptical galaxy with no gas. And that has a lot to do with the different environments. So in a cluster of galaxies, there's a lot of different processes that try to turn your blue galaxies into red galaxies by trying to get rid of the gas so that it can't form stars. So it's different physical processes. I like these, this sort of schematic indicating the different processes. And we won't go into too much detail about the physics of it, but there's different mechanisms that try to either strip the cold gas away that you can't form any stars anymore, or you get something like starvation, where nothing as such happened to the galaxy. It just uses up all of its gas, and eventually it doesn't accrete new gas, so it just turns into a red galaxy. So that is why we study these galaxies in clusters, is we want to get a view of how these galaxies transform, because this is, well, the two main types of galaxies that you get, the blue star-forming galaxies and the red elliptical galaxies. But you get other types of galaxies as well. But these are the two main types of galaxies that you get. And we want to understand this dramatic transformation process that can turn a spiral galaxy into a big elliptical galaxy. So if you want to understand or observe this transformation in progress, you want to look at the different components of the galaxy. So the galaxy has stars and gas, and to look at the different components, you need to do different telescopes. So in optical, you can nicely see the stars of the galaxy, and in a radio telescope, you can nicely see the cold gas. But you can see in this galaxy, for example, it fell into a cluster and it's now stripping the cold gas. And the cold gas gets stripped out, but the stellar body of the galaxy is still completely intact. So these different components in the galaxy respond in different timescales to these processes in the cluster. And that is why we want to study what we call multiple tracers. We want to look at the stars and the gas of the same galaxies. And we can do that with if we use both SALT and MeerKAT. So we studied this Fornax cluster. It's a very nearby cluster in the Southern Hemisphere. So that's what makes it easy to study, is it's extremely nearby. So we can study all of the galaxies in the cluster in a lot of detail. But it's also interesting because if you look at a better picture of the cluster, then you get a lot of cluster galaxies here. So let's just, these empty dots that sort of regularly spaced, this is just pointings for MeerKAT, so you can ignore that for a moment. And this is also not a very deep optical image, so we can only see a few galaxies, but there's quite a few more galaxies in the cluster. But this is the cluster, and then just outside of the cluster, there's a galaxy group. So it's less galaxies, but they're also gravitationally bound. So it's called a group of galaxies, and it's actually falling into the cluster. So the cluster is, well, as we're looking at it at this point in time, the cluster is still busy to assemble its mass. So that's what the other reason why the Fornax cluster is extremely interesting, because galaxies can transform from the spiral galaxies to the elliptical galaxies in the cluster, but it's also already happening to some extent in the group, even before it falls into the cluster. So if you look at what this group looks like through MeerKAT, through the radio telescope, then this is the three sort of central galaxies around the group. So those three there. And the blue in this image just shows you the cold gas that we observe in the radio. And the pink shows you the ionized gas, so the warm gas that we can see in optical images. If you look at H alpha, like a narrowband filter image at H alpha, for example, you will see these ionized gas. And you can see that there's a lot of clouds of gas that's not necessarily connected to a galaxy, that's being stripped away from the galaxy. And you can see that sort of the different components or the different phases of the gas also correspond. So you get a lot of overlap to where the cold gas is and the warm gas. So if we look at the whole group, this is Fornax A, that's this group that's falling into the Fornax cluster. So you can see this is a bit of a better optical image in the background. So you can see more galaxies. And then all of the blue contours that we plotted overhead, that's the cold gas that we see with MeerKAT. So those three galaxies that I showed you, that's around here. And you can see, but it's quite extensive, these little clouds of cold gas that's being stripped away from the galaxies. And even if you look at just the galaxies, you can see there's sort of a different stages of their evolution. So if you look at these galaxies here, it's actually two spiral galaxies together. But you can see they still have this extensive cold gas disk around the galaxy. And this one, for example, started to lose its gas. So you can see there's this tail of gas. And then you can look at this one, for example. So there you can see even, well, relative to the size of the galaxy, you can see an even bigger tail of cold gas that's being stripped away. And then you can see, you can get these galaxies that has a very sort of small, compact disk of cold gas that's sort of left over. So these are three different stages of how these galaxies are actually losing their cold gas. And we can actually look at it, we can measure the amount of cold gas, and we can categorize these galaxies into different stages of their evolution. So then we can go, well, we can call it, for this study, we called it early pre-processing, because it's still in a group, it's not even in the cluster yet. So we call it pre-processing of the gas, and we can see early pre-processing like in this galaxy, or ongoing pre-processing like in these galaxies, or advanced pre-processing where you've almost completely lost all of your cold gas. And then we can take some of these galaxies, and now we can go to salt, and we can observe optical spectra of them, and then you can say something about what the stars look like, or the star formation history is in these different galaxies that you now know is in different stages of losing their gas. So we can take optical spectra of these galaxies, because we also know exactly where the cold gas is now. So even if it's only a slit for an optical spectrum, it's not a data cube, you can still position your slit that you can see you really probing the stellar body of the galaxy and the cold gas. And then what we want to study from the optical spectrum is you get an absorption spectrum like this, that looks a bit like what I showed you previously in the talk. And then what you want to do is you want to measure signatures of the stars at different stars of different ages. So you can measure, for example, hydrogen alpha, and that tells you how many very young stars there are. So how many stars formed in the last 10 million years. But if you look at the G minus R color of the galaxy, for example, so you take a G band image and an R band image and take the difference for the color, that tells you mostly about the stars that formed over the last billion years. So if you can measure these different sort of indicators, you can see how much the star formation changed over time. And you can, for example, plot it in a diagram like this. And then if your galaxy is just aging, it's just burning its gas, there's nothing much happening to it, it follows a certain track on this diagram. But if some of the environment of the group or the cluster then causes these galaxies to lose their gas much earlier and faster, then they will follow different tracks on these diagrams. So again, I won't go into too much detail here. The point that I really just want to bring across is that we use the telescope simultaneously to look at the different components, and then eventually you will just want to build up a picture of how this galaxy evolved during time until you get the galaxy what it looks like today. Okay, and then lastly, I'll just show a few pictures of some of the smaller telescopes we have at Northwest University. So I think this is the part of the talk where you know probably more than I do about the telescopes. But outside of Potchefstroom, the university has a farm in the Vredefort called Nooit Gedacht, where we have this optical telescopes that's permanently installed there, and it has a CCD imager, and it also has a small spectrograph. And we use it mostly to take students out, third-year students, for their practicals. And we also use it a bit for outreach as well. So not so much for research, but for student training. And in Mafeking, on the other campus, we have an almost identical facility. It's actually on campus in Mafeking itself. So it's not as dark as the site that we have in the Vredefort Dome, but it's accessible. So it's used a little bit more for outreach opportunities. Okay, this is the sort of aerial picture of the Nooit Gedacht farm. So you can see there's that building over there is where the telescope is. Then there's a small classroom or sort of control room. And then you can see we recently started to build 4 radio dishes. So there's one and there's one over there. But there's 4 of them and they're about 3.6 meters across diameter, these dishes. And it's not quite finished yet, but we want to build a small radio telescope, so a radio interferometer that we can also use for student training. Okay. And in the last telescope that we have, that I didn't have a picture on hand, but we have a small solar telescope on the roof of the physics building that has hydrogen filters that you can look at the sun mostly. So you can look at sunspots and solar flares and things like that. And that's it. And if you're in the Potchefstroom vicinity, just come and say hi, drop into the department and come and talk to us. And I'll stop here. Thank you.
Thanks very much, Ilani. What a fascinating talk. Can we get going with some questions? Pierre de Villiers is with us, and he's our resident expert on star formation and how they work and so on. Maybe he's got a question, Pierre?
Well, first of all, just say thank you for a very interesting talk. The modeling that you referred to, is it a standard model that you took over from someone else, or did you develop it in-house? Because I deduced by matching observations with theoretical models, which is quite cool.
So the ingredients of the model, if I go back to this image, so the ingredients like stellar tracks, for example, and stellar spectra, so that all comes from other people. So it's from stellar libraries and things. But what we do ourselves is we put it together in a certain sequence, and then we say, okay, if you form so many stars at this age, and then again so many stars at this point, what sort of spectrum you look like, you build up. So we put it together, but the actual ingredients that go into the modeling is fairly standard and available.
Thank you.
Sorry, Pierre, you finished? Or? Okay, can I then just ask that mind-boggling number you mentioned earlier on, that 5 times 10 to the power 12 solar masses? That's the mass of a galaxy, is it?
Yeah, so that's the mass of the galaxy, but I should say it's the total mass.
Okay. But I mean, that number, we're used to hearing numbers like the number of stars in a galaxy is sort of maybe 100, 200 billion. I mean, that's bad enough. But this, as far as I can understand, that's a 5 trillion solar mass, total mass.
Yeah, so they are humongous, but a component of that is the mass from dark matter. But there is also a absolutely humongous amount from the actual stars.
All right. I just saw an interesting video, an interview by, what's that guy's name, Neil deGrasse Tyson, interviewing somebody called Catherine Friesman or something like that. She had a story about dark matter annihilating its forming dark stars. Apparently quite a number of years ago, and then somebody said to her, okay, that's a good model for explanation for these multi-billion solar mass black holes that are formed, because nobody had any idea how they might form, and this explained that quite neat. Do you have an opinion on that?
Not really. I know this is a very active field of research, is the actual black hole. If I go back to this, so the actual black hole in the center, how it accretes its gas, and then the jets coming out, and that's a whole separate thing. But
is that part of your work? Is it a completely different focus?
Well, it has implications for us. So dark matter is important for all of us, especially in galaxy evolution, and especially if you work in clusters of galaxies where there's quite a lot of dark matter, and it's not equally distributed. So it has a mass profile. So you do want to understand the dark matter, but exactly how it forms and what it consists of is an entirely different field that even goes into particle physics. But what we can tell about dark matter is only the indirect things that we can observe, like the orbits, in these orbits of the stars in the galaxy. If you observe that, then you can also deduce the mass in the center, so the mass of the black hole. But we can't say exactly what dark matter is. We can just say what it affects, or how it affects our galaxies.
Yeah, it's just that I'd never heard of anything called a dark star before, and
yeah, the dark star.
Never knew that there was a theory that a cluster of dark matter in contact with itself can annihilate So I don't know. It was all very interesting to
But
me.
that I've heard of before, but a dark star is also, it's new to me. Yeah.
Okay. Apparently, this was like more than 10 years ago that they started with this or something.
Yeah, I think these theories come up and and go. There's always, well, obviously what we have at the moment, we can't explain it, so people are really thinking about out of the
Yeah,
box.
it's all theory, of course, but apparently it's quite well supported with observations and so on. Okay, thanks. Anybody else got a question for this? It's quite an
Yes.
intensive session, this, but is that Peter?
Yes, thank you, Ilani, for a fascinating talk. I just have a question about the formation of stars at the beginning of the universe. I think one can safely assume that these stars only consist of light elements like hydrogen and helium. And as they progressed and evolved, then stars started obtaining heavier elements. So to what extent can you use the metallic content or the heavy element content of these galaxies to determine the age of these galaxies and which generation they are, perhaps as they evolved through time?
That is a good question, and that is something that we do spend a lot of time on. So you can see we know where the different elements are, so we can measure these elemental abundances. And then, as you say, we know that, well, stars start off as just hydrogen, and then they burn heavier elements up to where they consist basically of a carbon core, and then these shells of heavier elements. But then what complicates this is, then if you have a supernova explosion, and it's a certain type of supernova, then it expels, some of the elements. But then if you have different types of supernova that comes from stars that evolve slower, and they explode at a different time scale, and they expel different elements. So if you measure all of these elements and you get the ratios of the elements, so for example, how much iron to magnesium you have, then you can basically say, you can use it as a chemical clock as such. So you can say how quickly the star formation happens, or if it's still happening and you get stars that evolve quicker and a certain type of supernova. So that's something that we do spend a lot of time on, and you can learn a lot from the metallicity or the chemical abundances, especially if you can, not only measure the metallicity, but the separate elemental abundances.
Okay. And another question, to what extent can you use James Webb to assist and complement the telescopes that you're using on the surface of the Earth?
Yeah, so James Webb is extremely interesting because it's at some of these wavelength ranges in the electromagnetic spectrum that we've never had access to before. So sort of mid-infrared that we really cannot observe from the ground through the Earth's atmosphere. So we do, I'm not leading any projects, but we are involved in a few projects that is using James Webb data. But at the moment, they're concentrating a lot on these extremely high redshift galaxies, because that's, they're breaking records as far as they go. So every month there's a higher redshift galaxy that they observe. So there is a lot that we can do, but I'm a bit more interested in what the galaxies look like today. But they are finding extremely interesting things for what the galaxies look like quite early in the universe.
Right. Thank you.
Did you by any chance cover the early, evidently in some of those early James Webb galaxies which have been observed, there were oxygen in some of them which shouldn't have been around in those first getting close to the Big Bang theory. Is it casting some doubt on Big Bang or putting some more questions out there?
Yeah, so that is interesting. So James Webb has found these galaxies that they call red dots or something. So it's a galaxy that's already quite red, and that we know only happens after some time. But they found it very early in the universe, and they're also extremely compact. And then they have these elemental abundances that you really only expect to form later. And there's quite a lot of them. So these galaxies are quite abundant. But then they started to take actual spectra of these galaxies, and then they look also at the emission lines in the spectrum, and then they found these very broad emission lines that tells us that you either have sort of extreme star formation, or you have it comes from the black hole, the ionization from the black hole. So I think initially when they started to see these galaxies, it was a puzzle, and people thought it's going to break the standard cosmological model and the Big Bang. But then they started to take spectra of it, and then they saw, well, actually it's not as massive and as compact as it appears. It's just that the emission that you see comes from either extreme star formation or the jets of the black hole that, you know, makes it look like, you know, something that it's not. So I think at this point, people are sort of leaning more towards we can actually still explain it with what we have. But we never, you know, you never know, it can find something that we can't explain with our models. So.
Any more questions? Yeah. So you don't get any access to, I suppose, access to James Webb.
Well, we have to apply, and it's large international teams.
Yeah.
It's extremely competitive.
Everybody, the whole
everybody
globe
wants-
trying to get in on one thing.
Everybody
Yeah.
wants to look at their favorite
Yeah.
object.
Good. All right, and when SKA starts growing, is that going to make a big difference to your research?
Yeah, I think then it's really we already saw over the last few years the landscape has changed, and even my own personal research, it's changed a little bit from being a lot of optical stuff to being more combined multi-wavelength stuff to also use the MeerKAT data. And because, you know, people specialize in different things. So as I specialize in optical spectroscopy, there's radio astronomers that specialize only in the cold gas, and we really have to work together to figure out what's happening. But of course, they've already started building SKA the mid-frequency, the first dishes is going up. So it's not that far off. It's only, we've been talking about SKA for so many years now, but now it's really, you know, maybe, you know, between 3 and 5 years away. So now we really have to start to think bigger and you know, what we're going to look at and how we're going to handle all of the data and all of that.
Yeah. Fascinating times ahead.
It's almost scary if you think about the data that MeerKAT is bringing in, and then you exponentially blow it up, and that's what SKA will bring in.
Yeah, they said they hadn't invented the storage system yet that could handle it. I don't know how far they've got with that now.
I think they're thinking about all sorts of clever ways to you know, take out the useful segments of the data that you can essentially throw something, you know, some
Yeah,
use.
I'm sure they're going to use AI in there
That's
somewhere.
not really what you would want, but no, they are working on that.
Yeah, this 3D spectrum thing box is quite an interesting thing. I'm still trying to work out how that works, but anyway, looks very interesting.
Now you really get a lot of information, because otherwise you will miss any sort of spatial information. You can tell a lot about just one single optical spectrum, but you really want a picture of what is happening in the galaxy.
All right, any more questions for Lonnie? What are we doing on time? It's nearly 7, not too bad. 5 to All right, I'm going to say thank you very much for a very fascinating presentation. We had quite a good group of participants here this evening. So thank you to everybody for taking part, and those who asked interesting questions. I thought the questions were great. So we hope to hear from you in the future again, how it's going and so on.
It was nice to talk to you, and thank you for the invitation as well.
Thanks very much.
Thank you. Thank you very much.
Thanks and good night.
Night.
I'm gonna stop the recording now. Johan, if you could just hold on for a minute. Find the stop button here.